Now we are in the chapter number 6, that is about the okay, seems here is chapter number 5, that is about inner product space, and we are studying what we call orthogonal complement, and we apply that with the special case, that is for fundamental subspace of a matrix. I repeat that, given m by n matrix A, then we have 4 fundamental subspace. The first one is row space, and in the slide here you have not seen the row space, but however it is a column space of A transpose. I will not explain to you, but we have a row space, column space, null space, and left null space, and they are subspace of Rm and Rn. For example, column space and left null space, they are subspace of Rm. And row space and null space, they are subspace of Rn. And those subspace are orthogonal complement of each other. Here, for example, what in the red box here? The column space of A. If you take the orthogonal complement of that, you will get the left null space of A. Similarly, if you take the row space of A and you take the orthogonal complement, you will get the null space of A, and so on. And more than that, when you consider column space of A and left null space of A, they are subspace in Rm. But more than that, Rm will be the direct sum of column space of A and left null space of A. And similarly, Rn will be the direct sum of the column space, row space of A and null space of A. Yeah, that is what we know about the case for fundamental subspace of any matrices. And we use that in doing with the least square problem. So what is a least square problem? Least square problem saying that, suppose that we are given a system of linear equation Ax equal B, and suppose that the system is inconsistent, means it does not have an exact solution. It does not have exact solution only in the case B does not belong to the column space of A. In that case, we need to find the value of x so that the distance from between Ax and B is minimum. I say is as small as possible. In case we find that x hat, we will call it the least square solution of the system of equation here. And we know already Ax is always belong to the column space of A. And in the column space of A, the vector which is closest to B, it means the distance between that vector and B is minimum, is the orthogonal projection of B on the column space of A. That is, we need to have A x hat, I call x hat is a square least square solution. A x hat must be equals projection of B on the column space of A. And we have some more analysis how we can get the projection of B on column space of A. We will get the following thing. In order to find x hat, I mean x hat is a least square solution of that. In order to find that x hat, we need to solve the system of linear equation here. A t multiplied by B will get a column matrix. A t multiplied by A we get a matrix here. And now that becomes a system of linear equation, and we call it associated normal system. And I believe that in last week during some tutor class, many of you have done some exercise on this kind of least square problem, least square solution. So that is the on for the lecture number 5, and we continue with the lecture number 6. The lecture number 6 deal with what we call the linear transformation. So what is a transformation? First, we consider a function t, or the function t, that is a map, or I call it mapping or something, or corresponding t from v to w. V and w, both of them are vector spaces. It will send each vector inside v into one vector inside w. V will be called the domain and W will be called the codomain. Or in the picture, you see the domain is here and the codomain is out there. And you see the range is something smaller inside here. The definition for the range is here inside. The range of T is a set of all image of vector inside V. Here. And the image is here. And on the definition, the name here. I will not repeat it here. But what I want to repeat for you in this slide, that is a notion of a linear transformation. I abbreviate it by LT. Suppose that T from V to W is a mapping from vector space V to the vector space W. T will be called a linear transformation if it satisfies two axioms or two properties, like on the screen. I insist to use that. You can remember when you want to verify something to be a vector space, sub-vector space, you need to verify only two properties, property number 1 and property number 6 in the definition of a vector space. So here as the same, you need only to have you need to satisfy only two properties, and it is very easy to verify. And for a linear transformation T from V to W, we have 4 properties here. And I insist that the most important thing, the most important property, that is the property number 4. However, property number 1 is a very practical. It says that a linear transformation is always send zero vector of domain into the zero vector of codomain. That is very practical, very useful when you want to show something is not a linear transformation. You just only to verify if t of 0 equals 0 or not. That is very easy to calculate t of 0. And one observation case, that is a case on the slide here. Suppose that A is an m by n matrix. Now we define a function denoted by t. T is defined by the formula like that. And it is obviously will be a mapping T from Rn into Rm. Why is that? If you take A to be Z1 and you multiply by a column matrix here, or we call it a vector inside Rn, the reason will be a column matrix, or we call it a vector inside Rm by formula is here. You can do it by yourself. So obviously that one is a mapping from Rn into Rm. And our observation saying that the map T defined like that is a linear transformation. It is a linear transformation. It's very important thing. And here is an example. If we consider A to be 3 by 2 matrix like that, you multiply with a column matrix, you will get a column matrix here. And very easy for you to verify two properties here. That is exactly the property of operation on matrices. The examples for you, that is a rotation defined like that. And also the projection. The projection, if by formula you get that one, and by matrix you get that one. And it is exactly a linear translation T given by that one. You multiply A by the coordinate x, y, z, you will get that x, y, 0. We continue with the notion of the canon and the range of any linear translation. Suppose that T from V to W is a linear translation. Then, if we consider the set of on vector V inside V, so that T of V equals 0 will become the canon of T. And we denote it by that thing. Or by formula, you get that one. The canon of T is the set of on V, so that T of V equals 0. And we have the examples, or not only example, but just only to consider with two special linear transformation. The first one is zero transformation. In that case, the canon of T equals on the domain. Why that? Because that zero transformation send on the vector of V to the zero vector inside W. So because of that, by definition, the canon of T will be the whole domain here. But in case T is an identity transformation from V into V, the identity means it sends V to V itself. So the canon of T now is 0 because it's the only one vector sending to 0. That is a 0 vector here. So in that case, the canon of T is 0. We have observation saying that if T from V to W is a linear transformation, then the canon of T is always a subspace of the domain, the subspace of V. And that subspace or the canon of T sometimes will be called the non-space of T. Non-space is a very familiar name for us. So then you can see, in case T is given by a matrix, I mean T is given by the formula Tx equal A multiplied by x, then the canon of T is equal to the solution space of A. Solution space of Ax equals 0, or the canon of T is exactly the known space of the matrix A, or by definition, you can see it here. So we see the known space of T and the known space of the matrix A as the same in case the linear transformation T is given by a matrix A. On the other hand, I mean on the codomain, on the W, we can define the range of a linear transformation T. The definition is already done before, or here. You can look back once again. The range of T is here. We call it the range. The name and the notation are the same. And once again, the range of a linear transformation T is always a subspace. But now it is a subspace of the codomain, not of the domain. Or if you look at the picture here, the big round here is a domain, and the big round there is a codomain. Inside the domain, we have the canon. Inside the codomain, we have the range. And also, once again, in case the linear transformation T is given by a matrix, I mean Tx equal A multiplied by x, then the range of T will be the column space of A, nothing new. So you see for linear transformation T, if it is given by a matrix A, then the canon and the range we'll go back to the notion we studied already 7 weeks ago. That is something about the four fundamental subspace of a matrix A. Next, we give some name, the rank of T. That is the dimension of the range of T. The rank, and that is the dimension of the range. The nullity of a linear transformation T, that is the dimension of the canon of T. And once again, in case linear transformation T is given by a matrix A, then the rank of T equals the rank of the matrix A, and the nullity of T equals the nullity of A. Then we get back on we study already for a matrix A. And also because for matrix A, we have the relation between the rank and the nullity. So similarly, for a linear transformation T, we have similar relation. That is, suppose that T from V to W is a linear transformation. It goes from an n-dimensional vector space into a vector space W. Then we have the rank of T plus nullity of T equal n. N is the dimension of the domain. After that, we study what we call the one-to-one and onto mapping. So what is the one-to-one? The one-to-one, that is the map, something like that. It means that one vector in the range can be the image of only one vector in the domain. And that example, that picture illustrated a map which is not one-to-one. Why that? Because in this case, that vector in the codomain, that is lying in the range of T. But however, it is the image of two different vectors inside the domain. So that it is impossible, it is unacceptable for the definition is here. So that is one-to-one. Or you can remember it by a formula like that. If we have TU equal TV, it implies that U and V must coincide each other. And we have a onto. Onto is a function from V to W, so that any vector in the codomain will be image of something from the domain. Or you can say another word, that is the range of T equal the whole codomain. Then now that the definition for the one-to-one and onto, that is for any function, for any map. But now if we consider only linear transformation, then it is very easy to verify map linear transformation to be one-to-one or to be onto. How we can do it? The first claim says that if T from V to W is a linear transformation, and then T will be one-to-one if and only if it has a canon consisting of only one vector, is a zero here. It means only in the case canon of T equals zero. And also, how about the onto? Suppose that T from V to W is a linear transformation, and suppose that W, I mean the codomain, is a finite dimensional vector space, then T will be onto if and only if the rank of T equals the dimension of W. The rank of T is the dimension of the range of T, and range of T is a subspace of W, and it requires that the range equal codomain, then the dimension of the range equals the dimension of W. That is what we have here. And the last one, even even one-to-one and onto are two different kind of mapping. But however, in case T, our mapping T is a linear transformation, and both domain and codomain are vector space of the same dimension, then T is one-to-one if it is onto. It means that in that case, if T is one-to-one, we know we can imply that T is onto. And if we know T is onto, it implies that T is one-to-one. That happens only in the case domain and codomain are of the same size, and T is a linear transformation. That is. The last one, that is the notion of isomorphisms, đặc cấu. A linear transformation T from V to W will be called an isomorphism if it is one-to-one and onto at the same time. And now suppose that we are given two vector space V and W, and suppose that there exists an isomorphism between two vectors from V to W. Then we say that V and W are isomorphic to each other. And then we have the claim saying that two finite dimensional vector space V and W are isomorphic if and only if they are of the same dimension. We are going to have an example on it today. And finally, we finish class last week by the homework like that, the projection, the diagonal, and the reflection. And also today we are going to have some more homework on C maps here. So that is what we studied last week, and we continue the class today from this point. Now, here is our homework from last week. But before the homework, I claim to you that two vector space are isomorphic to each other if and only if they have the same dimension. And here is an example for you. We have 5 vector space here. The first one is a 4 space. That is a dimension 4. We know already. The next one, we consider M4 by 1. That is a space of on 4 by 1 matrices. That is a column space, a column matrix which has 4 entries. And the third one, we have M2 by 2. That is space of on 2 by 2 matrices, square matrix of order 2. It also has a dimension 4. And the next one, that is space of on polynomials of degree less than or equal to 3. It has dimension 4 because it has a standard basis consisting of 1 x squared and x cubic. We have 4 vectors in the basis. And the last one will be the set V. That is a set subset inside R5, consisting of x1, x2, x3, x4, and 0. And xi can be any real number. And that will be a subspace of R5, of the 5 space R5. So we now, in the example here, we have a 5 vector space of dimension 4, and they all are isomorphic to each other. So next, we begin to study what we call the matrix of a linear transformation. So what's that? Last week, we know already, we defined already what is a linear transformation between two vector space. And also we consider special case, that is in case a linear transformation T is given by a matrix A. Now I consider it again here. Suppose that T is given by formula like that, or you can write it in this form: T of x equal A multiplied by x, with A to be that matrix. And if you multiply that with the column matrix here, you will get that formula. So why we need that? We have that formula is enough. But however, why we need to have the matrix form of a linear transformation T? We have three reasons for that. The first one, it is simpler to write because usually we write only this part. We did not write that part. Second one is it is just a little simpler to read because we read Tx equal Ax, did not read on the coefficient here. But most important thing, it is more easily to be adapted for computer use. That is, we can input it in the computer by looking at the matrix here like an arrow data or something like that. So because of that, today we study what we call the matrix of any linear transformation. The first one, the first part, we consider standard matrix for a linear transformation. Now suppose that T from Rn into Rn. Suppose that T is a linear transformation, and now we calculate T of E1, and we write down the coordinate column here. T of E1 is a vector inside Rm, so it has M coordinate, and we put it in the column like that. And we continue by T of E2, we write it in the column like that one, and up to T of En, we have a column like that. And I repeat that E1, E2 up to En is a standard basis for Rn. I will not repeat what is E1, what is E2, what is En. You know that in Rn you have a standard basis consisting of n vector denoted by E1, E2, En. Now we have n columns like that. Now we put them side by side together. We put them side by side together like that. We get a matrix A. The first column is TE1, the second column TE2, and the last column TEN. You get that thing. That is a matrix M by N matrix. It is, we call it the standard matrix of T. The standard matrix of a linear transformation T, like that. And you can verify that the matrix A satisfies that is T of V equal A multiplied by V if we write V in the column matrix like that. It is explained here. It is already written in the slide and you can read it by yourself. And here is some example for you. Now, you consider the map or the linear transformation T from R3 to R2 defined by the formula like that. Then, in order to find the standard matrix for T, you need to calculate T of E1, T of E2, T of E3. If you apply the formula like that, you will get T of E1 to be that, T of E2 to be that, and T of E3 to be that. And now we write it in the column. You get that one. The first column is here, second column is here, third column. Now put them side by side. You will get A to be that. It is exactly the standard matrix of T. And you can verify A multiplied by that, you will get again. That is the formula. Yeah. And the last remark here, I would like to tell you. You will have a lot of exercise please write down the standard matrix for some linear transformation. Then the way to do that is you look at the formula. T is given by the formula like that, and it has 1, 2 coordinate. The first coordinate will be 1x minus 2y plus 0z. So we take on the coefficient here. When you put it there, 1 go here, minus 2 go there, and 0 go here. So that is the first row of the matrix. Second row of matrix coming from second coordinate of the formula, and it is 2x plus 1y plus 0z. So 2 going here, 1 going here, and 0 going here. That is the way we write down the standard matrix for any linear transformation. Now here is some other examples. We consider a linear transformation T from R2 into R2. That is a projection on the x-axis, and it is obviously the projection on the x-axis is given by the formula like that. T of x, y will be x0. Lying on the x-axis means the y coordinate is always 0. Now A, the standard matrix will be T of E1, T of E2, and T of E1 is here, T of E2 is here, and we get that thing. And finally, A to be that one. Then the remark for you to see. Now we define already what is the standard matrix for any linear transformation T from Rn into Rn. Now we consider special case. That is the case of zero transformation from Rn into Rn. Then in that case, standard matrix will be zero matrix of the sign m by n. And in the case identity matrix, in the case of identity transformation from Rn into Rn, then in that case, the standard matrix will be the identity matrix I of order n. That you can verify by yourself. And now is homework number 2. As I promise you, once again we go back to three maps I introduced you in the homework last week. We have a three map. The first one is a projection. The second one is a diagonal map, and the last one is a reflection. Then you are invited to find the standard matrix of those mapping. Let me continue. Now we continue with the notion of composition. Composition of two maps, T1 and T2. And in the composition of two mapping, you need to remember that the order of two maps is very important. Why that? You can look at the picture here. Suppose that we have a linear, first you have a mapping from Rn into Rm. Then you have another map, say T2 from Rm into Rp. So we have two mapping like that. Whenever you have that, you can define a new one going from Rn into Rp by, first we go from here to there by T1, and then we continue going from here to there by T2. That is very easy to imagine, or by formula you can get this one. Given V inside here, first you apply T1, you get T1 of V, that is something. Right? And then we apply T2 to go, continue to go up to here. So that is That is the notion, the definition of composition of T1 and T2. And in that case, I denoted T equal T2 composed to T1. And you should remember that the domain of the composition will be the domain of the first map, the domain of T1. Like that. And what I want to claim is following. Suppose that here we define composition for any mapping T1 and T2. But now we consider the case when both T1 and T2 are linear transformation. T1 here from Rn into Rn is a linear transformation, and T2 from Rm into Rp is also a linear transformation. And I suppose that the standard matrix of T1 is A1 and the standard matrix of T2 is A2. Then we have the following things. The first one, the composition T we define above, defined by that, is again a new linear transformation. And the second one, because T is already a linear transformation, so what is the standard matrix for A? Then for T, the standard matrix A for T now is given by multiply A2 by A1 like that. That means A is a product of A2 and A1. Once again, I require you to remember the order of A1 and A2. You need to write A2 first and then A1. It is quite similar to that one. And here is some explanation for you why that is a linear transformation. And again, in order to verify something to be some mapping to be a linear transformation, you need only to verify two properties: T of U plus V equal TU plus TV, and T of CV equal C times T. So, and then you can verify that the standard matrix for the composition, and anything is written already in the slide on the Buddha. You need to read it by yourself. However, I give you some remark that in general, T1 composed T2 is different from T2 composed T1. And the example is here. Now suppose that we consider T1 and T2, they are linear transformation from R3 into R3. And defined by, the first one is here, T1 to be that, and T2 to be that. Then you are required to find standard matrix for two composition. The first one is T2 composed to T1, and the second one will be T1 composed to T2. First, we write down the standard matrix for T1. It is here. Once again, you look at the formula here, you will get immediately without any calculation. That one is a standard matrix for T1. And what is the matrix for T2? Again, we look at the formula here. You get that thing. So we have two standard matrices for T1 and T2. Then we apply what we have already on the previous slide. Then the standard matrix for T equal T2 composed to T1 to be that. And if we multiply them, you get that one. On the other hand, the standard matrix for T prime equal T1 composed to T2 will be that one. And obviously, two matrices here are quite different. It means that T2 composed to T1 is different from T1 composed to T2. That is an example for you to show that in general, T2 composed to T1 is different from T1 composed to T2. Now we are going to define what we call the inverse linear transformation. Now suppose that we have a T1 from Rn into Rn and T2 again from Rn into Rn. Both of them are linear transformation. And I suppose that they satisfy two equality here for every vector v inside Rn. And if you want to look back at that, you will see, look at that, it is easier for you to write as follows. The T2 now is a mapping, a linear transformation from Rn into Rn, but I want to write it as arrow like that one. T2 going like that. That is T2 going from here. So then, if you consider the T2 composed T1, it means that you go from here to there and then go back to here. And that equality saying, if you go from here to there and go back here, then you get the identity transformation. And also for the other side, it means that you go first from here and go there and then go back here. Once again, you get the identity transformation on the codomain here. That is a meaning of two equality here. So I want to explain to you it like that. But now you see, suppose that T1 and T2 satisfy that, then we will call T2 to be the inverse of T1. And in that case, the linear transformation T will be said invertible. It is an invertible. Then we have the following remark. In case T1 is invertible, means we can find T2 satisfying that, then we can find only one T2 satisfy that, and because of that, the inverse is unique and is always denoted by T to the power minus 1 here, and we call it T inverse or inverse of T. So now we have a following equivalent claim. Suppose that T from Rn into Rn is a linear transformation and it has standard matrix A. Then we have the following equivalent claim. T is invertible. T is an isomorphism and T then the matrix A is invertible. A is invertible. So we have three things, three equivalent things like that. And more than that, suppose that T is invertible with standard matrix A. Then the standard matrix for T inverse is A inverse, is inverse of the matrix A. And example is here. Now we are given a linear transformation T from RC into RC. It is given by the formula like that. Then you are required to show that the first one, T is invertible. And then you need to find the inverse of T. So how we can do it? The first one, you need to write down the standard matrix for T. It is here. Once again, I repeat to you, the way to write down the standard matrix for T, that is, you take the formula here. The first coordinate is 3x1 plus 2x1 plus c2 plus x3. And then you take 2, the coefficient 2, you put it here. The coefficient 3, you put it here. And the coefficient 1, you put it here. So we get the first row of A. Similarly, for the second row is here, because here the coefficient is C1, so we get C1. And the last row give you 2, 4, 1. That is the standard matrix for T. Next, we need to find the A inverse by using Gauss-Jordan method. If you can find it, then T is invertible. If you cannot find it, you say that T is not invertible. So here is a way to do. We write A here, and on the right hand side of A, we write the identity. Now we apply the Gauss-Jordan elimination. We can change the first part into identity. Then the second part here is A inverse. It means that T is invertible transformation, and the standard matrix for T inverse is A inverse, and the A inverse we find it here already. Then the T inverse will be like that. T inverse multiplied by T inverse of V equal A inverse multiplied by V. A inverse is here, and V is coordinate x1, x2, x3. And if you multiply them here, you get the column coordinate here. Or if you want, you can write it in a formula like that. It is here. So that is anything we should study in for the standard matrix. And we now we take a short break, and after that we continue with the lecture number 6 here. So we take a break now, please.
Phát Tây Ban Nha Hoa Kỳ mày ơi, 6 phút nữa.
Oh, sorry for disappear for some time. I have a visitor for asking something. Can you continue now?
Yes.
Okay. We continue from here. Before the break, we study what we call the standard matrix of any of a linear transformation from Rn into Rm. But now we are going to study the matrix for any linear transformation in any case. I mean here, suppose that V and W are vector space of finite dimension. Please remember the finite dimension. And I suppose that we have a basis B of V and basis B prime of W. And I suppose that B consists of vectors V1, V2 up to Vn. Now, if T from V to W is a linear transformation, then we can do as follows. First, we calculate T of V1. T of V1. And T of V1 must be inside W. And because W has a basis B prime, we write down the coordinate of TV1 according to the basis B prime. And that coordinate column will be right here. Similarly, we can find the coordinate column of TV2 relative to the basis B prime. And we put it in the column here. And we do it with on n vector V1, V2 up to Vn. We get n column here. Now we put them side by side. We put them side by side. We get an m by n matrix here. We put them side by side and we get a matrix here. We denote it by A and we call it the matrix of the transformation T relative to the bases B and B prime. B on the domain and B prime on the codomain. We have two things. And that matrix A satisfying that formula. T of V equals A multiplied by V. You should pay attention to the coordinate according to which basis is. And here is some examples. Now, suppose that we consider T going from R2 into R2. And suppose that T is given by that formula. Now, suppose that on the domain here, we are given a basis B like that. And on the codomain R2, we are given the basis B prime to be that one. Then you are required to find the matrix T relative to the B and B prime. How we can do it? We just follow the definition we did in the previous slide here. We need to find T of the first vector in B and T of the second vector in B. We get that one. And after that, we express that in the basis B prime. We get that one. Or if we write it in the column, we get the column, the first T of 1, 2 is here. T of minus 1, 1 is here. It is that. So put them side by side, we get the matrix of T relative to the basis B and B prime. It is here. We get that column, we get that. And next, we continue that. That is, in the previous, we get the matrix A already here. That is the matrix of T relative to the basis B and B prime. Now, the exercise here, or the example here, require you to find T of V. And suppose that V is given with a coordinate like that. Then what we need to do? V is with coordinate 2, 1 inside here. But the first step, we need to write it, the coordinate of V according to the basis B. B consists of two vectors, Z and Z. So we express V into the basis B. Then it has coordinate 1 and -1. So we say coordinate of V relative to the basis B will be 1 minus 1. Then we apply the formula. Then T of V inside B prime equals A multiplied by V. A we know in the previous slide, and V of B we know is here. So we multiply them together, we get that one, C. That is the way we do with the exercise, with the example. Or you can verify T of V equals that. Again, we get that one. And in that case, B prime should be remember B prime to be that one. And you can verify by some other way. So I will not do it here. Now I summarize. The matrix of T relative to the basis B and B prime is following. T is a linear transformation from V to W. B is a basis for domain. B prime is a basis for the codomain. And the matrix of T relative to the basis B and B prime is the following one. You calculate T of V1, T of V2, T of Vn. You get n column, coordinate column. You put them together side by side. You get a matrix denoted by A. That is a m by n matrix, and we call it the matrix of T relative to the basis B and B prime. And it satisfies the formula like that. That is a summary for what we defined already. In the case, I like to tell you, in the case, the domain and codomain are the same, means V equal W. And in that case, usually we choose basis B on both sides. B is on the domain and the codomain. And in that case, the matrix A will be called matrix of T relative to the basis B, because now we have only one basis for domain and codomain. We don't have to say some more thing. But more concrete, if you consider the special case, that is the T is identity transformation, then you can choose any basis for V. Any basis for V. The matrix of T is always the matrix of T relative to any basis B is always the identity matrix. You can verify it by yourself. You can calculate T of V1, T of V2, and T of V. It always get like that. So you put them together, you get the identity. So I repeat once again. If we consider the identity transformation from V to V, you choose any basis for V. The matrix of T relative to that basis is always identity. And always identity matrix. Next, I repeat to you what is a transition matrix and similarity. And in transition matrix, we know already, we studied already 7 weeks ago. Chuyển cơ sở, we studied it already. But similarity, that is a new one. Similarity in Vietnamese is đồng dạng. Now I begin right now. Suppose that we have a T from V to V is a linear transformation. It sends V to T of V for any vector V inside the vector space V. Now, suppose that first, I suppose that we are given a basis B for the space V. B consists of V1, V2, Vn. And then the matrix of T relative to the basis B will be given by this way. You calculate that TV1, TV2, TVn. And we write down the coordinate column, we put them together, we get the matrix A. And also, the matrix A satisfying the following formula here. The transformation T and the matrix A satisfying that thing. And now, suppose that we are given another basis B prime of W1, W2 up to Wn. That is another basis for V. Then, matrix of T relative to B prime will be given by the same way here. Just only replace V1 by W1, V2 by W2, Vn by Wn. And we replace the basis B by the basis B prime. So we have n coordinate column. We put them together, you get A prime. And also we have the formula T and A prime is related to each other by that thing. Then you see, you have A and A prime. They are matrices of the same linear transformation T, just only relative to different basis. Then we would like to know what is the relation between A and A prime, how they are related to each other, A and A prime. So it is here. Now because we have two bases here, two bases B and B prime, then we have a transition matrix from B prime to B. Ma trận chuyển cơ sở từ B phẩy sang B. Transition matrix from B prime to B. It is defined by this way. And with that, we have the following formula. The coordinate of V in B equals P multiplied by the coordinate of V in B prime. And also we have another transition matrix back from B to B prime to be defined like that. And usually that is denoted by P inverse. And obviously, and also we know already that P inverse here is exactly the inverse of P here. And also we have another formula. Okay. Now, together with anything here, we can see the relation between A and A prime. It is here. You look at the diagram here. At the bottom, that is a map, or that is a linear transformation T. And we consider on both sides V and V here, we consider the basis B prime. And because of that, the matrix will be A prime. That is that line here. And at the top here, you have, that is the same mapping T, the same linear transformation T, but on V, on the domain and codomain here, we consider the basis B. And because of that, the matrix of T relative to the basis B will be A. Okay, here. That is A already. So here we have the matrix A, here we have the matrix A prime. But how we can choose, how we can move from V, coordinate of V with B prime, into V with the coordinate B? That is here. That is here. So that we will get a matrix P. And similarly, changing from the coordinate of T, coordinate from B into the coordinate of B prime, we can apply the P inverse is here. So that is the way we can relate A and A prime together. Next, we consider the following slide. Once again, I consider the diagram like in the previous slide. We have two ways to get from V with the coordinate in B prime into TV with the coordinate in B prime. The first way we consider it is a direct way. That is, we go directly from here to Z. And because of that, we have that formula. Or by the red arrow here, we call it the direct way. But on another time, we have the way indirect. Indirect means we go first from here, we go here and go there and go back to here. So that is a C step to get here. And we call it the indirect, or we can see the big red arrow is here. And if you look at that, that is a composition of C map. And C map is linear transformation. So the matrix for that will be that, you see, P inverse multiplied by A multiplied by P. So you see, the first way you get here, the second way you get here, and also the right hand side are the same. It means that the left hand side are the same. Means we have the relation A prime equals P inverse multiplied by A multiplied by P. That is the relation between A prime and A. So now I summarize. A and A prime, they are matrices of the same linear transformation in different bases, and they are related to each other by the formula like that one. And P inverse are transition matrices we defined already before. And here is some example. Suppose that you are required to find the matrix of matrix A prime for the mapping T. T is given by that formula. And you are required to find the matrix A prime for T relative to the basis B prime, like that. So how we can do it? We have two ways. The first way is here. You just only to find T of the first vector, T of the second vector, and then yes, and then you input them together, you get the matrix, and T of the first one will be here. T will be that one, and we express that in the basis B prime. You get that one, and of the second one, we do similarly. We get that one. So we have two columns. Put them together, you get A prime to be that one. But however, you can do another way. Another way, the first step, we need to find standard matrix for T. It is very easy. That is a matrix of T relative to B, to be that one. And it is here. And next one, transition matrix from B prime to B to be that one. And transition matrix from B to B prime to be that one. That is very small size matrix, so it is very easy for you to find the inverse. Then we apply the formula A prime equal P inverse multiplied by A multiplied by P. You get that one. That is the same reason as in previous slide. So you see, we go two ways, give the same reason. And also in the previous slide, that is a direct way, and here is an indirect way. You can see. Next, suppose that B to be that and B prime to be that. Suppose that both of them are basis for 2 space R2. Now suppose that we know already that the matrix of T relative to B to be that one, and you are required to find the matrix of T relative to B prime here. How you can do it? It's very easy. You need to find the transition matrix from B prime to B and from B to B prime and multiply them to with A, you get A prime. Here, the transition matrix from B prime to B, we know already how you can get it, and it is here. And the transition matrix from B to B prime will be that one. Then A prime equal P inverse multiplied by A multiplied by P. We get that one. So that is a way for to do with that. With the reason from the previous slide, because we have A prime here. Then you are required to find V of B by n, that you are required. And suppose for the vector V, which for the vector V having the coordinate here, that is the coordinate of V relative to the basis B prime, and you are required to find that thing. So it is here, V of B, I mean V of B. The coordinate of V relative to the basis B equals that, and we have V of B prime is here, P to be that one, so that will be that thing. The next one, we do the same way. We have A already, so we multiply them together, you get that thing. And the last one is here, TV of B prime, you can get that thing. Now you need to change from the basis B into B prime. So we need to apply the P inverse to get that one. So that is what I want to tell you, or you can verify with that one. Now we are going to define what you call similar matrices. Suppose that we are given two square matrices A and A prime of the same order n. We say that A prime is similar to A if there exists an invertible matrix P of the same size like A and A prime, and such that A prime equal P inverse multiplied by A multiplied by P. So what does it mean? The meaning of that is, from previous slide we see that the matrix of the same linear transformation in different bases, they are always similar to each other. That is what I want to tell you. And here are some property for similar matrices. So I can go very fast here. A is always similar to itself. If A is similar to B, then B is similar to A. And if A is similar to B and B is similar to C, then A will be similar to C. That is anything you can verify by yourself. Here are some explanation. It is already written in the slide on the Moodle. You can read it by yourself. Here are examples. A and A prime like that are similar because if you choose P to be that, you can verify A prime equal that one. And the next one, A and A prime here also are similar because if you take P to be that one, you can get the same formula here. So that is an example for similar matrices. Now, just I want to invite you to look at that example. Suppose that A is a matrix of size 3 by 3. That is, suppose that it is a matrix for T relative to the standard basis, or you can say A is a standard matrix for T, like that. Now you are required to find the matrix for T, but relative to a new basis B prime, as on the screen. So what we need to do? First, we need to find the transition matrix from B prime to the standard matrix. It is here. And the transition matrix from B from standard from the standard to B prime in equal that. And then A prime will be that one, P inverse multiplied by A multiplied by P. So if you multiply C matrix C here, you will get that one. And there is one thing I would like to insist here, and I will leave it for the lecture number 7. That is, here A prime now is in diagonal form, is already is a diagonal matrix. So once again, you can see here the matrix, the linear transformation T has a matrix A in standard basis. But if you choose another basis, here I choose a basis B prime, like that, then the matrix for T relative to B prime is in the diagonal form. And next lecture, we will study about that. We will try to transform any matrix into the diagonal form, like that one. That it has a name, diagonalization. In Vietnamese, chéo hóa một mặt trận. Okay. So anyway, that is the job of next week and after next week. Now, before finishing the lecture number 6, I tell you what is the advantage of a diagonal matrix. Suppose that D is a diagonal matrix like that, then it's very easy for you to verify that D to the power K will be again diagonal matrix, which entry will be D1 to the power K, D2 to the power K, and Dn to the power K. You can try it first with the K equal 2, and then continue with K equal 3, and so on, and you will see it is very easy. The next one, obviously, you take the transpose, nothing changed. And the last one, in case Di on the entry is non-zero, then D will be an invertible matrix, and its inverse to be diagonal matrix like that. Its entry equal 1 over D1, 1 over D2, and 1 over Dn. So that is a finish of the lecture number 6. And we continue right now with the lecture number 7. Yeah. You see the title. The title of the lecture is Eigenvalue and Eigenvector. So what's that? Because we studied already eigenvalue and eigenvector several weeks ago. But now I repeat for you. It's the main purpose of the lecture number 7. That is about diagonalization and orthogonal diagonalization. Now, first, I repeat for you what is eigenvalue. Suppose that you are given a square matrix A of order n, and we want to find the non-zero vector x in Rn, so that A multiplied by x as a column matrix will get a multiple time of x, or by formula it is as follows. A is an n by n matrix, lambda is a number, x will be a non-zero vector in I. If three things here satisfy Ax equal lambda x, then the number lambda will be called eigenvalue of A, and x will be called the eigenvector of A corresponding to the eigenvalue lambda. That is what we studied already. Or by geometry, you can see it here. And the example here is already in we study already. A to be that 2 by 2 matrix, x1, x2 to be the standard unit here. And both of them are eigenvector. The first one, x1, is eigenvector corresponding to eigenvalue 2. The second one is here. It is eigenvector, but now it is corresponding to another eigenvalue, the eigenvalue -1. And that one I don't think that we studied already. That is, now suppose that A is a square matrix of order n. And suppose that we fix an eigenvalue lambda of A. Then the set of all eigenvector of lambda together with 0 vector will be a subspace of Rn. And we call that subspace the eigen subspace of lambda. I insist that here we need to add 0 vector in the set of all eigenvector. Why that? Because eigenvector, we require that it must be non-zero. But a vector space, a subspace, always contain the 0 vector. So we need to add that here. You can see it by example later. And here is some explanation. Once again, I repeat to you that to show that something to be a subspace, you need to verify only two properties, property number 1 and property number 6, like that. What you are seeing on the screen here. And here is some example. If you consider A to be that, you need to find eigenvalue and corresponding eigenspace. So you are going to see what is the eigenspace now. A like that. Now we consider any vector v with coordinate x and y. You multiply them together, you get minus x and y. If you look at the coordinate here, the point on the plane with coordinate x, y, now will be changed, will be sent to a new point with the coordinate minus x and y. It means it has the same y coordinate, same coordinate y here. But the x coordinate will be changed from x into minus x. It means that by geometry, it means that, oh, I'm sorry. It means that if you multiply a vector x, the matrix A with a vector xy, we get a reflection. Or if I want to look at it, you will send xy into minus xy here, minus xy here. And if you find the eigenvalue and eigenvector, you will see on the vector lying on the x-axis will be eigenvector corresponding to the eigenvalue -1. And on the vector lying on the vertical axis here will be eigenvalue corresponding to the eigenvalue 1. But however, the 0, I mean the origin here, is not an eigenvector because 0 vector cannot be an eigenvector. And that is the reason why we need to add 0 here to get the eigenspace. That is eigenspace corresponding to lambda 1 equal -1 is that straight line. And eigenspace corresponding to lambda 2 equal 1 is the whole vertical axis here. That is an example to show you what is the eigenspace. And finally, I repeat for you how we can find eigenvalue and eigenvector of any square matrix of order n. Suppose that A to be that, then eigenvalue of A will be a number lambda. Bạn nào đó tắt hộ cái mic ấy ạ. Eigenvalue of A will be the eigenvector of A. I'm sorry, A is an n by n matrix. Then eigenvalue of A will be a number lambda satisfying that equation. And the eigenvector of A corresponding to lambda will be a non-zero solution of that one. That is what we studied already. I just only to repeat for you. And once again, why we need to explain why we get that? Because AX equal lambda X will implies that lambda I minus A multiply X equal 0. And it is already is a homogeneous system of linear equation. And we know already that such a homogeneous system of linear equation which has non-zero solution if and only if the determinant of lambda I minus A equals 0. And because of that, lambda must satisfy that equation. And that equation which has named characteristic equation of A. And the left-hand side of that is a polynomial of A, a polynomial in variable lambda, and we call it characteristic polynomial of A. That is what I repeat for you. And here is some example. I leave it for you to read because I want to stop class today here. But before finishing the class, I have something to show you now. I suppose that all of you want to see this one. Yeah. That is something about here I inform you something about the midterm exams. The midterm exams will be taken place this Saturday morning. And once again, you will be divided into 3 groups as in the test exam. That you know already. Because we know that some of you will be absent because of học quân sự training somewhere. So those people will take the midterm exams at some later time. That will be informed later, not now. And now the time scheduling for each group as on the screen. You need to remember that. And now there is some more requirement for you. The first one, you need to log in at Zoom to take the roll call điểm danh and to get the password to the exam on Moodle. Now the exam will be provided with the password. So you need to go, when inside the Zoom, you need to go into the room of your tutor class. And then I require that you switch on your camera on the time you do the test, on the time. The Zoom link will be sent to you by email on Friday, not today, not tomorrow. That is on Friday. And the time, the duration for the test will be 60 minutes, and you have to finish 16 questions of the test, and you need to finish it before the close time. The close time is here. Here for the first group, here's for second group, and here's for the third group. That is on. I want to there is one more thing. You can go to the Moodle to do the exams if in case you get password from your friend or by some way. But however, if you do not show up in Zoom, your test will be drop out. Nếu các bạn cứ xông thẳng vào Moodle làm bài mà không vào Zoom để điểm danh và bật camera lên, thì bài thi của các bạn trên Moodle sẽ không được chấm điểm. It will be a drop out. So that is all about the midterm exam. So just please ask.
Em thưa thầy là những câu hỏi của bài kiểm tra này có nếu mà làm xong thì có thể quay trở lại được không, hay là làm xong?
No. Yeah, it is quite like in the test exams. You don't have the option to go back when you push on the next.
Vâng, cảm ơn ạ.
Professor?
Yes, please.
Which lecture this midterm cover?
It will cover up to the chapter, the lecture on vector space. Not about the inner product, but on the vector space.
Thank you, Professor.
Yeah. Some more questions, please. So if no more questions, so we stop today here, and I wish you good luck for the exams. And
Professor, can you upload this today lectures onto Moodle?
Lecture number 7. Oh, okay. I will upload it this evening. Okay.
It's okay. Thank you.
Professor, can you upload the midterm test into the email?
What?
Thấy thầy đăng cái nội dung về midterm lên cái Gmail rồi.
Nội dung midterm là cái quái gì ạ?
The required. I think he refers to the required option for the midterm.
So I will put an announcement on the Moodle this evening, and everything requirement for the midterm for the midterm exams will be on the Moodle this evening. Okay.
Okay.
Something else? Okay, so goodbye you and good luck for the.
Professor.
Yes.
Can we see those our score after finishing test?
No. You will get reason later for that.
Thank you.
See you.
Goodbye, Professor.
Bye bye.
Goodbye, Professor.
Bye.
Bye you on.
Như